sketch that proof by giving some motivation for what the proof should look like. So instead of going right into the document, let's start with this. So we want to show this. So this is going to be entirely a sketch, and then we'll actually write it down. And what things did we prove last time? So I proved like some of the properties of absolute value because I said I'm going to need these properties exactly. And those properties were items in the list, 4 and 7. So the things that I presumably will want to use. And I'm going to change some variable names.
Is there a reason for the change, or?
Well, okay, I guess these are x's anyway. Okay. Just to avoid using like the same names over here, because maybe I'll want things to have different jobs. So those are the things I know, there's the thing that I want. So let's try to walk with that. And maybe I'll leave a number of these. This was item 4 on the list, this was item 7. So do one of those things seem to give you something that might be useful? So this one says, yeah.
I feel like there's some form of application of like 7 with, like an application of 7 somewhere. I'm not quite sure how.
Yeah, so this looks like absolute value of a thing is less than or equal to a thing. So what if we were to use this x plus y as our a and all this stuff as our b? That would tell us this is less than or equal to this, if and only if negative absolute x plus absolute y, but distribute the negative sign. So if we could prove this, then we would be able to deduce that. So here's the thing we want. Here's something that's equivalent. Maybe this is easier. How would you want to argue that that second inequality is true?
Yeah, but I just want to make sure that what I do I'm correct. So like you distributed negative throughout the alphabet.
Just go with this. Right. The thing that would be there before was negative absolute x plus absolute y. All right. Well, so if we can get the second, that last bottom blue line to be true, then the red line at the top will be true. Intuitively, why should that bottom blue line be true? Or the reverse. Not 7. I mean, 7 is what we just used. Does this have anything to say about that? Yeah, what if we could just pick out these terms? So if it was just negative x, and then negative absolute value of x, and absolute value of x, do those satisfy the needed inequality? What if it were just the terms with the y's? Does that? Yeah, and that's by item 4. Do we have a result saying inequality satisfies some additivity condition? I think we heard something like that last time. By the way, we haven't. Oh, neat. So I think that tells us what the proof should look like. So maybe one argument would be by 4, negative absolute x, less than or equal to x, less than or equal to absolute x, and negative absolute y, less than or equal to y, less than or equal to absolute y, by additivity. So, autofocus lock, by 7, absolute x plus y, less than or equal to absolute x plus absolute y. What do you think? Does that seem like a proof? Yeah, and we can now write it down if we want to. Any questions before I do? Yeah.
Is it possible to keep that page on the screen so I can keep translating it?
Sure. Because happily, the actual argument isn't long. All right, proof of the triangle inequality. Let F be an ordered field, A and B be in F. We have to show that absolute value of A plus B is less than equal to absolute A plus absolute B. The first thing we did in that sketch is, well, I guess it was the last thing when we were like pre-sketching, but the first thing in the actual argument is by claim 4. We have some inequalities about A and plus or minus absolute A, and B and plus or minus absolute B. We can add these inequalities and use the additivity property of inequalities. And apparently I have a reference for that. That's good. It follows that negative absolute A minus absolute B less than or equal to A plus B less than or equal to absolute A plus absolute B. And I guess we didn't do this step here, but it's written. So, I mean, if you want to get it into the form that item 7 literally needs, then you need to factor out the minus sign. But that's easy to do. So now we have something of the form A plus B is bigger than or equal to negative some quantity, is less than or equal to positive that same quantity. So the absolute value of A plus B is less than or equal to that quantity. And that's by claim 7. Neato. There's a proof.
But on the bottom line of the paper at the top, is that x plus y absolute value?
Yes. Okay. Although that's clearly actually x plus gamma, but it should be y.
Oh, it's gamma. Okay.
No, it looks like it should be y.
Okay.
I'm commenting as to my own Paul writing.
Okay.
Nice. Any questions about that proof? How many people would have been tempted in their own write-up to try to break that down into cases? Just prove it in each relevant case. Yeah, I guess that's a fine thing to do. Maybe the only reason not to would be because there would be lots of cases. And let's just try to enumerate them. So. I guess x could be positive or negative. So there's a branching. Y can be positive or negative. And you might think that's all the cases, but it's not really, because maybe you're worried about that too. But I guess if x is positive and y is positive, then you definitely have x plus y bigger than or equal to 0. So there are no more cases there. In the case that both of them are negative, then x plus y is less than 0. But in each of these subcases, there are two subcases. So it looks like in reality you need like 6 enumerated cases along with an argument why those are all the cases. It's not that bad, but this is short. And a short proof is often better. So, let's move on to the thing that's actually on the docket for today. And this is the notion of completeness. So, previously we've stated, right, and the homework assigned today consists of a single exercise. I want you to prove that. And maybe I'll give you the following hint that you might want to write down right now. So, you could make a case-wise proof, but there will be lots of cases. So maybe I'll give you the suggestion, instead, think about using the triangle inequality. And there's even like a comment of something that might be worth thinking about. Cool. So, completeness. So, I said before that the real numbers are defined by 3 words. The real numbers are a complete or field. Field means that you can add, subtract, multiply, and divide. And those operations work the way you'd expect. Ordered means there's a sense of inequality that plays well with plus, minus, multiply, and divide. Completeness somehow means that like there are no holes, there are no gaps. And you need that because there definitely is at least one ordered field that's not the real numbers. Can you think of a collection of things that you can add, subtract, multiply, and divide, and can compare with a sense of inequality? Yeah.
Rational numbers?
Rational numbers. And there are non-rational real numbers, so you definitely need something more. Here is that something more. And it'll take us longer to get to it, in that the actual statement of completeness won't come until there. Which is fine. There's just some stuff we'll have to build. So here's one definition which I think should be pretty straightforward. Let F be an ordered field. A subset X of that ordered field is an upper bound for that set X. If it's an element of that ordered field such that some stuff happens. And maybe to figure out what that some stuff is, let's like draw some things and say what it is. So let's see. Let's suppose that there's this number line, and I don't know, there's the set. Is that U an upper bound on that set?
No.
Here I know. Why not? Why do you think it should not be?
Because in order to be a bound, don't you have to be part of the set?
No. You don't have to be in the set to be a bound. Right, like, if you take all the numbers between 1 and 2, they're also bounded above by 7.
Oh, okay.
7 is an upper bound. It's just not a very good one. So an upper bound should be at least as big as everything in this set. Is this an upper bound? Why not?
There are elements that are greater than the upper bound, so it wouldn't be an upper bound.
Well, because there's
Being the ground that we haven't said.
yeah, there's stuff in the set that's bigger than that alleged upper bound, so it doesn't actually bound. Let's write down that definition. An upper bound is an element of that ordered field which is at least as big as everything in the set. So putting that into words, for everything in the set, for all little x in big X, it doesn't matter what you call the element of the set. For little x in big X, X is less than or equal to U. What do you think it should mean to be a lower bound? Yeah.
Precisely the opposite.
Yes. In that it'll be the same, but that inequality will be switched.
Yeah.
Groovy. So, a set is called bounded above if it admits an upper bound. It's called bounded below if it admits a lower bound. It's called bounded if it's bounded above and bounded below. So let's see some examples. So here are some sets. So I want kind of intuitive answers for now. Does it appear to be bounded above? If it does, then give me what you think an upper bound might be. The closed interval from A to B is all numbers between A and B. What do you think an upper bound on that set should be? Yeah.
Something greater than B.
Something greater than B.
Or greater than B.
Greater than anything bigger than or equal to B.
Yeah, cool.
Yeah.
So an upper bound can be technically the last element of the set as well, or like the highest element, let's say, for upper bound.
Mm-hmm.
Okay.
But let's.
I think we have the.
Yeah, that's definitely allowed. The
Okay.
upper bound might be an element of the set. If an upper bound is an element of the set, then, well, it's also like the maximum element of the set.
Yeah.
Do you think every set will always have a maximum element? What example are you thinking of? Yeah.
The empty set.
Okay, yeah, that's a good example. The empty set is false in many ways. How about like the open interval from A to B? Is there a biggest number that's bigger than A and less than B? No, like anything you pick will be just a little bit less than B. So you could go a little bit less than that, but a smaller little bit. So there are sets that don't have a maximum element, but still have upper bounds. Yes, like, I don't know. B is an upper bound. But even if you change those to strict inequalities, is B still an upper bound on that set? Yeah. It's, in fact, like a slightly more convincing upper bound. Let's jump around a little bit. How about this? The set of all elements of the ordered field whose square is at least as big as 1. Maybe draw a picture of what that set should look like on like a number line, be intuitive. Does that set appear to be bounded above?
Yeah.
I hear a yes. I also saw a head shaking no. And maybe we'll like draw a picture. So there's 0. 0 squared is not as big as 1. 1 squared is at least as big as 1. And in fact, everything over here is at least as big as 1. So I think the set looks something like this. Does that set have an upper bound? No, any number you pick, say that number, there's something bigger than it in the set. This is not bounded. What about the set of all numbers whose square is less than 2? Draw like a picture, if you will. Does that set appear to be bounded above? Yeah. What upper bound are you thinking of? Yeah. 4. 4 would do, right? If x were bigger than 4, then x squared would be bigger than 16, which is bigger than 2. That's too big. So 4 is an upper bound on that set. People feel okay? Well, let's talk through. Let's go up here. What is an upper bound on this set? Yeah.
I think what I said 4 instead of like 3, because I think I was thinking of the range being part instead of the domain, because we were talking in functions. Or I guess I was thinking of the image being instead of the pre-image being what the actual includes is about for upper bounds. Because 3 is an upper bound, right?
3, I think, is also an upper bound. But
Yeah.
what if we don't care what the upper bound is? What if we just care is there an upper bound? That would make me happy too.
Yeah.
In fact, I think 2 is probably also an upper bound.
Yeah.
But we don't care about getting the best upper bound right now.
Yeah.
So, I just want to make sure so that the second line there, is that supposed to be a 2?
Yeah, I replaced it with a 2.
Oh,
Yeah, it says 1 there, but I replaced it with a 2. Sorry, I should have had that all out of it.
oh, that makes this whole thing make a lot more sense.
So, but I think it's still worth it. Here's a claim. We've seen kind of informally that it's not a maximally efficient claim. We can do better as far as upper bounds go. But let's sketch the proof of this. So what do you need to show in order to show that something's an upper bound? You need to prove that for every element of the set some stuff happens. So to show that, what do we need to do? We need to consider any element of that set. And conclude, maybe the move up over there. Cool. How would you want to show that? Yeah.
Find the maximum value of what you can do in the set.
There are 2 problems there. I don't think that set has a maximum.
Okay.
And that's like, even if you think it does have a maximum, sometimes maxima are hard to come up with. Like you might think the max in that set should be the square root of 2. Does every Euler field contain the square root of 2? No. So there's something's difficult there. Let's try contradiction. So if you want to show this, let's suppose for contradiction. So if there's the thing you want to prove, what should you assume if you want to use contradiction?
Assume the opposite is true.
Yeah, what's the opposite of that? Yeah.
Greater than equal to?
Not equal to.
Yeah. Yeah, right. Because if Q were equal to 4, this would still be true. All right, so right now we have Q is in this set. And we have Q is bigger than 4. Let's try to get a contradiction. So on the one hand, because Q is in this set, what do I know about Q? No.
Is it that Q is equal to X?
So Q is one of these x's.
Yeah.
So the way to read this, Q is an element of this set, means this statement must be true about Q.
Okay.
So it must be alright. So I know that Q is bigger than 4 and Q squared is less than 2. Something fishy about that, right? Because what could I get out of Q being bigger than 4? What would that mean? Can you like square inequality if everything's positive?
Not sure.
Well, let's see. So let's see, Q squared, that's Q times Q. Well, by assumption, that's bigger than or equal to 4 times Q. Oh, it's strictly bigger than that. And that's bigger than 4 times 4, which is bigger than 2. Is this a contradiction? Yeah, so maybe I'll stop writing down because this is getting distracting enough. So we reached a contradiction. Q squared is less than 2 and Q squared is bigger than 2. That's a contradiction. So it must be that Q is not bigger than 4. That means that Q is bigger than or equal to 4. So what have we done? We considered any element of the set, showed it's less than or equal to 4. That means 4 is an upper bound. And that's the way a proof that something's an upper bound should look. Not all, it won't always be by contradiction, but you always want to assume a thing is in the set. You want to show it's less than or equal to be like an upper bound. How do people feel about that? Proof it. There'll be some opportunity to practice, at the very least in the homework. Nice. So let's keep on trucking. So in fact, let's begin with, let's prove something that I think will feel reasonably obvious. Let's let X be a subset of an ordered field F. I will denote by minus X the set of all X's such that minus X is in the set big X. Does that seem like a reasonable thing to call minus X? Yeah. I mean, I guess. Here's the claim. Let Y be an element of X. Y is a lower bound on X if and only if minus Y is an upper bound on minus X and all the different permutations of that. Oh, and all of those X. Chris. There, that's what I mean. So there are like 4 different claims here. Each and every one of them is an if and only if, so this really needs like 8 proofs. But all of those statements that you would need to prove look pretty much the same, right? Actually, those, yeah. Okay. So let's like prove one. So I will prove that if y is a something bound for x, then minus y is a something bound for minus x. And let's just pick one. If y is a, what type of bound would you like to assume? Upper. If y is an upper bound for x, then this theorem claims that minus y is a lower bound for minus x. So that's the only one I'm going to prove? Let's prove it. Let us assume that little y is an upper. So I guess this one is and that one is just a. So y is an upper bound for x. I must show that y is a lower bound for minus x. Fair enough. So that means I need to consider any element of the set minus x and show that that element of the set minus x is at least as big as minus y. So we will consider any element x, I call it x prime, doesn't matter what you call it, of minus x. By the definition of minus x, what do I know? So if x prime is in the set minus x, then what do I deduce? Yeah. Yeah. Negative that thing is in the set big X. Well, wait. So let's just write that down again. Negative x prime is in big X, and I know that y is an upper bound on big X. What can I deduce from those two things? If minus x prime is in big X and y is an upper bound, then yeah.
Is that y is greater than or equal to negative x prime?
Yeah. Right? And y is an upper bound, so it should be at least as big as everything in the set. Minus x prime is a thing in the set. There you go. All right, so let's keep in mind what we wanted. So what did we originally want? We want minus y to be a lower bound. So we want minus y to be less than or equal to this x prime. Does this inequality look like something you could turn into that inequality? Yeah, by doing what? I guess it's written, but like say it. Yeah, right? And that flips inequalities, so minus y is less than or equal to x prime. So let's just write down a summary sentence and actually see if we believe the summary sentence. We have shown that for every x prime and minus x, the inequality x prime is bigger than or equal to minus y holds. I guess it's written the other way here, but that's equivalent. Thus, minus y is a lower bound for the set minus x. How do people feel about that? So there's how proof of that something is an upper or lower bound just will look. You'll consider any element of that set. You'll show that it satisfies some inequality. If you assume that something is an upper or lower bound, then you automatically know that some inequality is true. People feel okay? Yeah.
I guess this might be rather silly, but like, how do we know we can multiply it by -1 to get what we want?
I believe that that's a thing that we proved about inequalities.
Okay, that's just something we could do.
Did we prove it? Well, it's written down. I don't know if we proved that the act of multiplying an inequality by a negative number flips the inequality.
No, not just the action, but like why we're allowed to do it. Is that just, I don't know if that's just a base axiom that just you can do.
I will find you a citation because it is in here, and I think I know which thing it is. It is in the bit about ordered fields. Multiplicativity 2. If A is less than B and C is bigger than 0, then A times C is greater than B times C. That says that multiplying by a negative flips inequalities. Is that exactly what we did?
Yeah.
Together with multiplying by -1 gives you the additive inverse,
Okay.
which is another theorem. But you'll notice I didn't cite any of them here.
Yeah.
So once we have these basic axioms and basic properties down, I'm going to not give citations for them, because that would make everything absolutely unreadable and tedious, and I don't expect you to either. Groovy.
Again, just a little the whole reason was just to get it in a form that works. That looks like what we wanted.
Yeah. Like this is what the end goal has to be.
Okay.
So then it's just, well, here's the thing I have. I've simplified that apparently as much as I can.
Okay.
There's what I need. Let's just look at that and look at what you want. How do you get from 1 to 2?
Oh, all right. Thanks.
Yeah. You should always, right. So during the course of a proof, you can get lost in the steps and be like, okay, this follows from this follows from this, and travel for a while. And at some point, you do have to look back at what are you trying to prove. Because it could well be that you actually got the thing you were trying to prove 5 sentences ago and you just kept on going. So do occasionally look back. Remember your goal. Remember what you're trying to do. Nice. All right. So there's what it means to be an upper bound. And you'll notice that I said a few times about how, okay, so that's like an upper bound. It doesn't seem to be the very best upper bound. 4 is an upper bound there, but like 2 would have been a better upper bound. Somehow like a smaller upper bound is better. It gives you more information. A bigger lower bound is better. It gives you more information. Definition. Let F be an ordered field, X be a subset of F. An element S of F is called the supremum, or least upper bound. The least upper bound should be the best upper bound. If S is an upper bound, and, well, the word least upper bound is suggestive. If S is the least upper bound, it should be less than or equal to absolutely every upper bound. 2, if U is any upper bound for X, then S is less than or equal to U. That seems like a reasonable, at the very least upper bound is exactly what that should mean. I think supremum sounds much more like an attempt at talking about the biggest element of the set. Not every set has the biggest element, but whenever you want to think about the biggest element, you want to think about the supremum. Because that's something that, well, spoilers, we will assume exists. Let F be an ordered field, X be a subset of F. An element I is called the infimum, or greatest lower bound. So if this were a class on complex analysis, calling something I would be a mistake. But this is not a class on complex analysis, so I'm perfectly fine calling a thing I. If I is a lower bound for X, and if L is any other lower bound for X, I is at least as big as L. So I'll use shorthand with some frequency. Instead of saying the supremum of X, I'll say sup of X, or int of X for the infimum. But there's a thing you'll notice there. That sounds like I'm thinking of these as functions, a function that takes a set and returns a bound. Well, for that to make sense, or for the fact that, like, the word the appears, these things had better be unique. Like, a single set has a great many upper bounds. So you can't say let u be the upper bound of this set. That's grammatically silly. So if you're going to say the supremum, or the infimum, they better be unique. Let's prove that they are unique. Let F be an ordered field, let X be a subset of F. If A and B each satisfy the definition of the supremum of X, then A is equal to B. Same thing with infimum. So let's try to prove this. So I'll try to proceed in two steps. So I'll prove two different inequalities. So let me see just a show of hands again. How many people have already taken the abstract? How many people have taken or are taking the abstract algebra class right now? How many people are taking both at the same time? Okay, you have a hard semester. Those of you who have taken the abstract algebra class already, you'll know that, like, in algebra, there's not like a fixed way to show two things are equal. There are lots of different ways. And, like, it all requires a bunch of work. If you're an analyst and you want to show two things are equal, well, you just need to show two inequalities. You need to show one is at least as big as the other, and the other is at least as big as the one. And then you'll have these two things being equal by the trichotomy law. So that's what we'll do. That's how we'll prove these two things are equal. And let's maybe write down up here the things that we know. So informally, A is the supremum of this set X. B is also the supremum of this set X. And I'll put the equals in quotes because I don't know that that actually makes sense. They both have all the properties. So that means A is an upper bound. B is an upper bound. A is greater than or equal to u, less than or equal to u, for every upper bound u. B is less than or equal to u for every upper bound called u. So, how can we put these two things together? So let's see, if I know that A is an upper bound and B is less than or equal to absolutely every upper bound, what's something you could deduce out of that? So if A is an upper bound, B is less than or equal to every upper bound, then yeah. Oh, neat. Is that one of the things we need to show? Yeah, let's go to the correct space and write down those bonds. So, claim 2. By assumption, that pen is getting a little bit low. B is, no, I'm using A as an upper bound. A is an upper bound on X, and for every, no, let's just write it this way. And B is the least upper bound, with emphasis on the word least. So A is an upper bound, B is the least upper bound, thus B is less than or equal to A. Do you think the argument that goes in claim 1 is going to look pretty similar? Yeah, I think so. So the reason that I wrote something on the board before I put anything there is because if I just started writing the argument in the space, I would have wound up putting the argument for claim 2 under claim 1, because I just would have started writing something. But here, there it goes. So the trichotomy law, once we fill in this space, which we won't, implies that A is equal to B. People feel okay about that? Since A is an upper bound and B is the least upper bound, B must be less than or equal to A. So let's get a feel for just some examples now. So here are some sets. The set of all things less than or equal to A. What do you think that the supremum of that should be? We're not going to try to be rigorous right now. Yeah. A seems to be, right? It's certainly bigger than everything in the set. Bigger than or equal to everything in the set, so it's an upper bound. But, if you take another upper bound, it should be at least as big as A. What if I take that loose inequality and relax it? Everything that's strictly less than A. What should be the supremum of that? Right, so maybe I'll do the pre-calc thing and draw it on a number line. So that's that set. What does it look like the least upper bound of that should be?
Something just greater than A.
Something just greater than A. Oh wait, but if you went just greater than A, I can go just a little bit less greater than A. So is your thing actually the least upper bound? No, mine beats it by a little bit. So you don't want something that's bigger than A. Well, how about A? Is A an upper bound on that set? Yeah, and I don't think you could get any upper bound that's smaller than that. Maybe it takes a few wants to argue. Okay, I'm convinced that has supremum equal to A. And maybe I'll go with, write down this one also. The empty set. So let's see. Maybe we'll check both things. Does that set have any upper bounds? I hear a no. I hear a head shaking. Let's maybe see a show of hands. Anyone for yes? Anyone for no? Okay. Let's write down the definition of upper bound with the empty set in mind. So a number is an upper bound for the empty set if for all x in the empty set, x is less than or equal to static. So the way to, let's write this means all x in F, if x is in the empty set, then x is less than or equal to static. All right, so this is an implication. It's an if-then statement. Is there anything that satisfies the hypothesis? No. There is nothing that satisfies the hypothesis. The hypothesis is always false. An if-then statement with false hypothesis is automatically true. Every purple unicorn is actually a dragon, because there are no purple unicorns to check. So this is true. So everything is an upper bound on the empty set. So let's just write down this sentence. Everything is an upper bound. So if you want to find the least upper bound on the empty set, you want the least thing out of absolutely everything. Is there a least element of an ordered field? Well, you could always subtract 1 from any field element, right? Make it a little bit less. So that's its bounded above, but it doesn't have a supremum. So there's no least upper bound. Let's see, with 4 minutes left, there's not enough time to prove this next theorem. We'll state the next theorem. And I think I'm going to jump to this, key axiom. So here is a theorem which we'll use a lot, so we'll actually prove on Monday, I guess. So it's unfortunately split up over 2 pages. For any set X, S is the supremum of X if and only if 2 things happen. S is an upper bound, so that's not exciting, because being the supremum means you're on upper bound. And for every epsilon bigger than 0, there is an element of the set X such that S minus epsilon is less than X. So this is now looking a lot more like trying to get at the supremum is the biggest thing in the set. If you look just a little bit to the left of the supremum, you'll always find things in the set. So there's an alternate definition that we'll use a lot. We'll prove it next time. But for now, and it'll take about a page, I think I want to close with the following axiom. So what does it mean to say an ordered field is complete? An ordered field F is complete if every set, except for the empty set, that has an upper bound has a supremum. Yeah. So everything that has upper bounds has best upper bound. And maybe now you believe that this is kind of like saying that there are no gaps in the real numbers. Right? Any set that has an upper bound, you imagine you keep on moving to the left, you get better and better upper bounds. You think you should be able to get a best one. This one says that as long as your ordered field is complete, it does. And here is the third and final axiom of the real numbers. The real numbers are a complete ordered field. And in fact, maybe I'll close with this remark. In truth, the real numbers are the complete ordered field. There's only one complete ordered field, and so it is the real numbers.
Is that by axiom, or can you prove that?
Remark 2.1.8, possible final product, that it is provable. So here's what I really mean by that. The real numbers are the only complete ordered field, in the sense that if math power is another complete ordered field, those of you who don't like using LaTeX, I'm sorry, but I'm going to use LaTeX abbreviations occasionally. Math power is that font. If you have another complete ordered field, then there's a bijection between math BDR and math power such that for every A and B in the real numbers, F of A plus B is F of A plus F of B, so F is what's called a homomorphism. For every A and B, if A is less than B, then F of A is less than F of B. F corresponds to the ordering. So there's a bijective homomorphism, so it respects the algebra, which also respects inequality. So those of you who have taken abstract algebra will know that means that this thing is an isomorphism. And so that's in the context of algebra, that's what it means to say two things are the same. So if you build the real numbers 2 different ways, you can get from one to the other, and they both contain all the same information. So there's the uniqueness, and you'll notice that I haven't proven that the real numbers exist, have I? Right. The real numbers are a complete ordered field. I have not verified for you that there exists a complete ordered field. That's something that maybe one should do, and these are both things that are viable final products. Construct the real numbers, prove that there's only one,